You know, it's pretty wild when you think about it. Your brain runs on about 20 watts of power. That's less than a dim light bulb, but it can smoke the most powerful supercomputers in the world at certain things. Our digital machines, they're amazing calculators for sure, but when it comes to learning, to adapting, they just devour energy. So that's led to this really revolutionary question. What if, instead of just programming computers, we could build them to actually think like a brain?
Okay, so to really get why we need these brain-inspired computers, we've got to talk about the fundamental limits of the computers we're all using every single day.
For decades, we've all been riding the wave of Moore's Law, right? The idea that our computers would just keep getting exponentially faster and smaller year after year. But that incredible ride is kind of slowing down. We're starting to bump up against the physical limits of silicon. And it turns out there's a huge architectural flaw in how our computers are designed that's becoming a major problem.
Right? And here's the core of the issue. Every computer you've ever used is built on something called the von Neumann architecture. See, the processor, the brain if you will, is over here, and the memory is way over there. And every single bit of data has to travel back and forth across this pretty slow connection. It's like a constant data traffic jam. And get this, it wastes up to 90% of a computer's energy, just shuttling data around. Insane, right?
So, if the old way is hitting a wall, what's the alternative? Well, the answer is to look at the most efficient and powerful computer we know of, the human brain. And this leads us to a completely new way of thinking about computer hardware.
You know, this idea isn't exactly brand new. Way back in the 80s, this brilliant engineer, Carver Mead, he proposed this radical concept. He argued that we shouldn't just be writing AI software that acts like a brain. We should be building hardware from the ground up that's structured like a brain. And only now is technology finally starting to catch up to his vision.
And this is neuromorphic computing. It's all about a fundamental redesign of the computer chip itself. So instead of a separate processor and memory, these chips have artificial neurons and synapses, the basic building blocks of the brain. They process and store information right in the same place. And just like that, you completely eliminate that von Neumann bottleneck.
And what's so cool here is that it's not just a computer science problem. It's this beautiful cycle. Neuroscientists study the brain, and that inspires new ways to compute. Then, engineers take new materials and devices to build these models. And the things they build, they actually help neuroscientists understand the brain even better. It's this incredible collaboration.
So how in the world do these brain-like chips actually work? Well, it all comes down to them speaking a completely different language. It's one that isn't based on constant streams of data, but on these little discrete spikes of information.
Right, so the AI that runs on your phone or in the cloud, it uses what are called artificial neural networks, or ANNs, and they communicate using continuous numbers, a constant flow. But neuromorphic chips use spiking neural networks, or SNNs, and just like real neurons, they communicate with these little discrete pulses of electricity, these spikes. A neuron only fires when it has something truly important to say.
This chart just lays it out so clearly. Traditional computers are sequential. They're driven by this constant clock tick, processing things one by one. But neuromorphic computers, they're massively parallel and event-driven. They only spring into action when a spike arrives. And that, right there, is the secret sauce to their incredible efficiency.
Let me put it another way. A traditional chip is kind of like an office where everyone has to shout and update every single second, whether they have anything new to report or not. It's just exhausting and super noisy. An event-driven neuromorphic chip, that's like an office where people only speak up when they have crucial information to share. It's quiet, it's efficient, and it wastes zero energy on silence.
Now, simulating a neuron isn't some one-size-fits-all kind of a deal. As you can see here, designers can actually choose from a whole spectrum of models. On one end, you've got these simple, computationally cheap models, and on the other end, you've got these incredibly complex models like Hodgkin-Huxley that are way more biologically realistic. It's always a trade-off between pure speed and accuracy.
And it's not just the neurons themselves, right? It's how you wire them all together. This creates this vast universe of design possibilities, from simple linear networks to these incredibly complex, interconnected webs that can even model things like memory and time. That flexibility is just crucial for tackling all sorts of different problems.
Okay, so we've got the how. Now let's get to the good part, the payoff. What are the real-world advantages of building a computer that actually thinks like a brain?
1,000 times. Yeah, you heard that right. For certain tasks like processing sensory data,
Neuromorphic systems can be up to 1,000 times more energy efficient than our absolute best conventional computers. That's not just a small improvement, that is a complete and total game changer.
And that crazy efficiency unlocks a whole bunch of other advantages. We're talking ultra-low power consumption, which means AI can finally run on small, battery-powered devices. We're talking real-time learning, so a device can adapt on the fly without having to call home to the cloud. And because the processing and memory are in the same spot, there's practically no delay, or what we call latency.
So why should you care about all this? Well, imagine a self-driving car that processes everything its sensors see instantly, using minimal power. Or think about advanced prosthetic limbs that can learn and adapt to their user in real time. Or what about smart medical sensors that can detect problems right on your body, instantly? This is the kind of future neuromorphic computing could make possible.
Now, this technology is incredibly promising, for sure, but it's not mainstream just yet. So let's take a quick look at where the field is today and the challenges it's still got to overcome.
Just look at this chart. We are at a really critical moment here. After decades of kind of slow progress, research in neuromorphic hardware has absolutely exploded over the last 10 years. The biggest names in tech, I'm talking Intel, IBM, you name it, they are pouring money into this. The momentum is just undeniable.
But there are still some major hurdles. We don't really have standardized hardware yet, and programming these event-driven, spiking networks, it's fundamentally different and a lot more complex than traditional coding. Plus, the software tools are still in their infancy compared to the mature AI platforms we have today. So solving these challenges is the next big step for the whole field.
So we end up back at this really profound question. What happens when computers can do more than just calculate? What happens when they can actually learn, adapt, and maybe even wonder? See, this is about more than just building faster or more efficient chips. It's a fundamental shift in what we think a computer can even be. It's a step away from pure calculation and toward a future of truly intelligent machines. The journey is really just beginning, and it is absolutely one worth watching.